Now let's take a look at the Newmark algorithms again and rewrite them for the multiple degree of freedom systems. First I will be looking at the explicit Newmark integration. So we said that the acceleration, this time it will be a vector, at the next time step will be equal to mass matrix plus delta t over 2 damping matrix is equal to the force vector for the n plus 1 time step minus damping matrix multiplied by the nodal velocities plus the stiffness matrix multiplied by the nodal displacements plus again the stiffness matrix multiplied by nodal velocities times delta t and minus delta t over 2 damping matrix times the acceleration plus delta t squared over 2 stiffness matrix times the acceleration, and this is in parentheses. And we said that this is our acts like a new mass matrix, so let's call it m hat, and this part acts like a new force vector f hat n plus 1, and at the end of the day we have m hat matrix multiplied by the nodal accelerations, and that's equal to f hat n plus 1. So that's the explicit Newmark integration. Now let me write the same equation for the implicit Newmark. Implicit Newmark integration so here we have u double dot n plus 1 multiplied by mass matrix plus delta t over 2 damping matrix plus delta t squared over 2 k, that's equal to fn plus 1 minus c times u dot n plus k times u n plus k times u dot n delta t minus delta t over 2 c dot u double dot n plus delta t squared over 4 k times u double dot n. Again, I can call this matrix m hat. Let's give different names. This is m hat explicit, this is m hat implicit. U double dot n plus 1 is equal to f hat implicit n plus 1. So let's do the same thing for this one. This is m hat f hat explicit for the n plus 1. Now, when we look at these m hat matrices for the multi-degree of freedom system, now in order to obtain the nodal acceleration, I have to do the following calculation. U double dot n plus 1 will be equal to m explicit hat inverse multiplied by u double dot n plus 1, and same here, u double dot n plus 1 is equal to m implicit inverse multiplied by, so this should be the f vector if explicit hat n plus 1, if implicit hat n plus 1. Now let's take a look at the properties of the M hat matrix. Now if we have free vibration, no damping, M hat will be a diagonal matrix, right? So it will have mass terms at the diagonals. And the inverse of M hat matrix will be very easy to calculate, very fast to calculate. They are just equal to 1 over M of the diagonals. Now this brings us a big advantage of the explicit Neimark algorithm. Let's forget about the damping for now. If we don't have damping, I don't have to do any matrix inversion. All I have to do is to multiply this F hat matrix with the inverses or 1 over M values. That's very fast. It's just matrix vector multiplication, and here we only have matrix vector multiplication and summations. So in this approach, this is a very expensive algorithms. So these matrix vector calculations are at the order of n. The factorizations are in the order of n cube. So you have, or it's a full factorization, or it's you have a bandwidth. You can just say that n times b squared. B is the width of the bandwidth. So the factorization or the inversion is computationally much more expensive than matrix vector multiplications. So when we have a free vibration case, if you don't have a damping matrix, then this is very easy, very fast to calculate. The other advantage of the explicit Neimark algorithms, here I don't have the stiffness matrix, so I don't have to calculate the stiffness at n plus 1 time step. I don't have to update the stiffness matrix. I can use the stiffness matrix for the current time step, and in this way I don't need any equilibrium iterations within the time steps. So basically we can just say that for the free vibration case, explicit Neimark algorithms computationally is much faster than the implicit Neimark. What is the downside? You have a limitation on delta t. This is conditionally stable algorithm. So when you look at the implicit Neimark, as you see, we have k here. Okay, it doesn't matter if you have a diagonal mass matrix. It doesn't matter if you don't have a damping here. What the main problem is, computational main problem is this stiffness matrix. So you always have a matrix to factorize. So you cannot simplify this calculation in the implicit integration. And for the nonlinear analysis, that's k at the n plus 1 time step. So you have to calculate the k in a correct manner for the in a nonlinear algorithm. So every time step you have to do equilibrium equations. So these are another comparison of the explicit and the implicit algorithms. Now we have an issue here because we talked about the damping matrix and we said that the damping matrix, right, C matrix, depends on not only the mass matrix but also depends on the stiffness matrix. So actually having this damping term here kills all the advantages of the explicit Neimark algorithms. So that's why you cannot just use this matrix to do to calculate the acceleration. Again, when you have damping, if you use the explicit Neimark, at every time step you have to do the factorization. Of course, here I'm talking about the nonlinear problems, because in the linear problems you do the factorization once. Since this matrices doesn't change with respect to time, you don't have to worry about them. So what to do? Now for this purpose we have the staggered explicit algorithms. So let's write down why we need it. So what I'm going to do is I will call this one the equation star. So in equation star, the mass matrix can be generated as a diagonal matrix. C matrix, however, is not a diagonal matrix. Thus, we have to factorize M hat matrix, which is a computationally expensive operation. So as an alternative, the nodal velocities can be computed a synchronous way at the half time steps. So what does that mean? Remember that this is 0, we have delta t, 2 delta t, and 3 delta t. That's how our algorithms work, right? At every delta t distance, we calculate the nodal velocities, accelerations, and the displacements. But in the synchronous methods, we calculate u and v at the u double dot at the classical time step, but for the displacements we will use delta t over 2, 3 delta t over 2, 5 delta t over 2 half time steps, and combine them with the delta t's and 3 delta t's by using the central difference approximations. So at the half time steps, we will be computing the nodal velocities, and from these nodal velocities we can calculate the displacements or the accelerations by using the central difference method. How? So I can say that u acceleration at n is equal to 1 over delta t velocity at n plus 1 over 2 minus velocity at n minus 1 over 2. Okay, so in other words, By using these two values, I'm calculating the acceleration at this time step. How can I calculate the displacement or the velocity at the half time step? That will be equal to 1 over delta t un plus 1 minus un. So in other words, I'm using these two displacements to calculate the velocities at this half time step. So that will be the central difference approximation. So if we just use this approach, our main equation of motion becomes equation of motion will have the following form: m times acceleration at n is equal to f n plus 1 minus k un plus u dot n minus 1 over 2 delta t minus the damping force. So if we call this part of the equation as our f hat, we can see that I can calculate the acceleration un as equal to mass matrix inverse f hat minus the damping force. And in that equation, the damping force can be calculated as the damping matrix multiplied by u dot n minus 1 over 2. So that's it. We will be calculating the velocities at the half time steps with this equation, and the accelerations can be calculated by using the velocities computed at these 2 points to get the acceleration of this point. Now let's see the flow chart so that we can better understand how it goes. The first thing that we have to do is calculate the acceleration at the 0 time step. That we can do by m inverse multiplied with f0 minus c times u dot 0. So initially we can assume that the velocity at the minus 1 over 2 second time step is equal to the initial velocity. So that's the way we start. Now I'm calculating the velocity at the next half time step will be equal to delta t multiplied by u double dot 0 plus u dot minus 1 over 2, or basically we can say that that's equal to delta t times u dot double dot 0 plus u dot 0. Again, I'm assuming that the velocity at -1/2 is equal to the initial velocity. Then I can calculate the displacement u1 as equal to delta t multiplied by the velocity, the half time step, plus the initial displacement. So for the first time step, we get everything. We have the acceleration, we have the displacement at the next time step, and I know the velocity at the half time step. Now I can calculate F1. Okay, after that we go to the next time step, next step. So the acceleration at 1 will be equal to m inverse f1 hat minus damping matrix multiplied by the velocity at 1/2. This will give me the acceleration at 1. So by using that acceleration, I can calculate the velocity at 3/2. That will be equal to delta t times u double dot 1 plus u dot 1/2. And from that I can calculate the displacement u2 as equal to delta t u dot 3/2 plus u1. So you will repeat these steps as many as possible, and you can calculate the velocities, accelerations, and so on. As you see, the main advantage here, I only have to invert the mass matrix. Even if I have damping in the system, inversion of the mass matrix is very straightforward. If you use lumped mass matrix, you only have the diagonal terms. You just revert the diagonal terms and multiply it with this vector, you get your accelerations. The stability condition is very similar to the explicit integration. This algorithm is also conditionally stable. You may need very small time steps. It's less accurate than the explicit integration, but computationally very fast. Implementation is very easy. Now we will be looking at the implementation of the new methods. This time we will take a look at the multi-degree of freedom systems. Now this is the governing equation. This is the equation that we are going to solve. So this matrix is the M hat matrix, and here I'm calculating that matrix. So these are all matrices. We have the effect of mass, damping, and stiffness matrix. This is the M hat. So we have F1 multiplied by the accelerations. This is F1. We have F2 multiplied by the velocities. So these are the coefficients of F2. It's written here. And the displacements are multiplied with the K matrix. So the algorithm is very similar to the single degree of freedom part. We calculate the F hat, and then we invert this matrix, or you can just factorize and calculate the accelerations, and from the accelerations, calculated accelerations, you calculate the velocities and the displacement for the next time step. So as we discussed, now this is not a diagonal matrix, so you have to do factorization. So if it is a nonlinear, you have to do the factorization at every time step because K changes, and also you have to do the equilibrium iterations at every time step. So that's the downside of the implicit integration. Now we also discussed the staggered explicit Neimark method. So this method is very straightforward, very easy. So we have the mass matrix. Now if you have the mass matrix as a lumped matrix, you will just the inverse of that matrix will be equal to 1 over the diagonals. So here I'm calculating the inverse of that matrix in a very simple manner. Now we have the f hat. We already derived that, and the f hat depends only in the stiffness matrix because we calculate the damping forces at half time steps. Okay, so that's fm. F hat, this is what I calculated here, and then I have to subtract the damping force. Here this is the damping force, and then multiply with the m inverse, you get the accelerations. So I multiply with the m inverse and I got the accelerations. Now in order to calculate the velocities for the next time step, this is the equation that I'm using. So it's right here. And for the displacement, I'm using the velocities calculated at the half time step, and that will be the displacement. So we repeat this procedure over and over again, and we can calculate the acceleration and displacements at the full time steps and the velocities at the half time steps, and the implementation is this much. Now let's work on an example problem. That's a very simple one. We have 3 springs connected in serial. Each spring has a stiffness equal to K. And at every node, I have a lumped mass equal to M. So this is a 3 degree of freedom system. This is the first degrees of freedom, second and the third degrees of freedom. And I'm applying a harmonic force from the third node. Now the frequency of the harmonic force is 8, and I define a damping ratio that's equal to 5%. And that's the equation for the harmonic loading. That's the stiffness matrix of the system, that's the mass matrix. Now here I'm calculating the eigenvalues of the system. Basically I'm doing this. M minus lambda k is equal to 0. So this will give me the eigenvalues of the system, and I got 3 natural frequencies. I got 3 degrees of freedom, 3 natural frequencies. The smallest one is equal to 1, the largest one is equal to 4.5. Now I will be constructing the damping matrix by using the Rayleigh damping approach, both mass and stiffness proportional. And in order to calculate these 2 coefficients, I will use the first and the third natural frequency, and for both frequencies I want 5% damping. So when I calculate the coefficients, A1 will be equal to 0.088 and A2 is 0.018. So by using that equation, I constructed the damping matrix. Now we know that the Rayleigh damping doesn't give us 5% damping at every frequency. Now according to this approach, I use the first and the third or 1 and 4.45 in this equation. So you see at 1.1 and 4.45 I have 5% damping. This is the damping with respect to W graph. Now for values smaller than 1.1 we have the mass proportional part, and for values after 4.45 now the stiffness proportional damping becomes more pronounced. Remember that this is the equation of this red graph. So basically what we are trying to do here is we define an interval. In that case the interval is with 1.1 and 4.45, and this means that I'm really interested in the vibration within this frequency limit between 1.1 and 4.45, because for frequencies smaller than 1.5 I got a rapid increase in the damping ratio which suppresses these vibrations, and after 4.45 the increase is not that rapid, it's linear, but again, for high frequencies, you got very high damping. So between these two, my damping ratio changes between 4 to 5%. Now we also discussed the stability limit for the explicit algorithms. We said that the delta t, the maximum delta t that we can use cannot be larger than 2 over the maximum, the natural frequency of the system. So basically this limit is equal to 2.2 divided by 4.45. So the delta t limit is 4.45. So this means that if I use a value larger than delta t value larger than 0.45 seconds, the results of the explicit algorithm should diverge, should go to infinity. So in order to test that, I have a sample case. I'm using a very large time step. The time step is equal to 0.5 seconds. And I'm solving this problem by using both implicit Neimark and the staggered explicit Neimark. So as you can see from the displacement graph, I'm plotting it for this middle node. But of course, for this case, the other nodes doesn't matter. For the middle node, after a while, I get very, very large displacement. The solution didn't converge to a result. Okay, so it's not a stable algorithm because of this reason. Now I know that my limit is 0.45. So for the second case, I use delta t as 0.2. This will give me a stable answer, but will it be a accurate answer? That's another question, as we discussed. So again, I'm solving the same problem with delta t equal to 0.2, and these are the results. This is the comparison of the implicit and the explicit result. As you see, we have some differences in the peak points, and it looks like the staggered algorithms has more vibration, high frequency vibrations. But the magnitude of the displacement, the maximums and the minimums, are not that different. They are different, but not very different. But when you look at the acceleration, we see a significant difference. The maximum acceleration of the implicit algorithm is around 2, but I get almost 2 times larger accelerations. And we see a significant difference in the accelerations. Again, I'm plotting these graphs for the second degrees of freedom. This is actually, we know from the finite element also, we are here looking at the displacement. The differences in the displacements might be small, but the accelerations are the second derivative of the displacement, which gives us much more big difference in the acceleration. This is something that we expect actually. So we know that 0.2 is a large times that give us lots of errors, so I'm reducing it. For the third case, I will be using a delta t equal to 0.01, and in that case you see the both algorithms give me the same result. So the explicit algorithm more computationally advantageous, and if I use a small time step, I got exactly the same results with the implicit algorithm for this particular problem. But of course, in this problem, we have a very flexible structure, so the delta t limit didn't make a big problem, didn't cause a big problem. But when you have a very stiff structure, using explicit algorithm will require significantly small delta t. Now also I want to take a look at the frequency responses of these two algorithms. So here we have lots of errors, and when we look at the frequency response, here 8 is my excitation force, so I see its effect, but it's more dominant in the staggered explicit algorithm. This is the first mode response, second mode response, and the third mode response. So we see differences in the third mode response of the both algorithms. The first mode and the second mode responses for the second degrees of freedom, of course, here I'm talking about, is almost the same, but the third mode response, we see some differences. But of course, when you decrease the time step, the differences vanish, so we get exactly the same frequency response of both algorithms. Now I also want to discuss the response of all the degrees of freedom. Remember that this is our structure. Let me draw it one more time. Two springs in serial. This is my first degrees of freedom, U1, U2 and U3, and remember that I'm applying the force to the third degrees of freedom. So as you see, when you look at the response of the third degrees of freedom, we see that the effect of the applied harmonic force is significant, but when you look at the second and the first degrees of freedom, it looks like they are somehow filtered, and I don't see the effect of that harmonic load that much. These are the displacement responses. Now let's take a look at the frequency response in the frequency domain. Again, I'm plotting it for this time for U1, U2 and U3. So the first mode is effective in U3, and the effectiveness of the first node decreases as you go to U2 and U1. As expected, I see the high influence of the applied force in the third degrees of freedom. In the second degrees of freedom it's less, and almost zero in the first degrees of freedom. So these two springs actually filtered the effect of the applied high frequency loading. So the response that I see in the first degrees of freedom is mainly coming from the natural frequency of the whole structure. So these are the effect of the natural frequencies of the whole structure. The second frequency, the natural frequency, is not effective in U2, so I see the effect of U1, the first mode, and the third mode mainly in U2. So that's mainly it about the integration algorithms, the dynamic analysis in the time history domain. So we have basically explicit and implicit algorithms. Implicit algorithms works at every delta t, no stability issues, whereas the implicit algorithms, you have a delta t limit. The explicit algorithms works very well if you have a very flexible structure, because the delta t becomes very large and you can use any time step you want, but it becomes a big problem in the very stiff structures. You have to use a very small time step, and sometimes using very small time step it takes all the advantage of the computational advantages of the explicit algorithms.